Okay, they are firing alpha particles at the gold foil. Okay, they are firing alpha particles at the gold foil. What are alpha particles? Do you even know what alpha particles are? Not yet. So alpha particles are 4,2 helium nucleus. Right, make sure you get this right. Not 4,2 helium atom. 4,2 helium nucleus. 4,2 helium nucleus. Okay. What's the difference between a nucleus and an atom? The spelling is different. What? What's the difference between nucleus and atom? Why? Same yeah, correct lah. So the 4,2 helium nucleus has no electrons. That's the thing. Alpha particles do not have electrons. They only have the 2 protons and 2 neutrons. Okay? Right? And we are firing it at the gold foil. Okay? And firing at the gold foil. So, yeah. Wait, they didn't go through this with you? Okay. What? I thought you said nuclear finished already? What the? Okay. All right. You need to know this. Okay. So, yeah, it's definitely will come out as a question one. So strange. How come they didn't tell you this? Have you finished nuclear in school already? Finished already, right? You? Not yet. You guys already finished last week, last term already. How about you? Nuclear finish already? Stop distracting Xavier lah. You know that he cannot pay attention one. Okay. So what's the idea of this experiment? You are shooting nuclei at a gold foil. Okay? That's kind of like what? Shooting ping pong balls at the wall. You understand? That's the concept of it. You would expect the alpha particle to bounce back. But instead of doing that, 90% of the alpha particles pass straight through the gold foil. Okay? Then the question is, what? Why? Why did the alpha particles not get, like, bounce back by the gold foil? What's wrong with the gold foil? Got a lot of holes. No, right? It's gold foil. And why did they use gold? Because it's more interesting. Gold is dense. So they're trying to show you that I'm trying to fire alpha particle at a dense metal. Okay? However, most of the alpha particles do what? Pass through. Right? The gold foil. Okay? Like ghosts like that. Pass through. Okay? But the reason why they pass through, right, is because, right, we would understand later that the reason why most of them pass through is because there's a lot of space between the gold nucleus. You cannot say that there's a lot of space between the gold atoms. Do you understand the context? Can I say that there's a lot of space between gold atoms? Why can't I say that? Why can't I say gold has a lot of space between the atoms? What? Yeah, gold is a solid, gold is dense, right? There's not a lot of space between the atoms. In fact, they're very tightly packed, right? The gold atoms are very tightly packed. But what they have a lot of space is between the nuclei of gold. So this is the nucleus, gold nucleus, gold nuclei. Look at that, these small little black dots here, right? These are the gold nuclei, right? So even though the atoms are packed very close to each other, right, the space between the nuclei is quite a lot of empty space, right? I mean, the electrons are there, but it's still quite a lot of empty space. You get this? Right. So of course, then the next thing will be, why is it like that? Right. So we have these 3 observations, right, that we have to come up with 3 explanations. Okay. Number 1, most of the alpha particles pass through undeflected. Some are slightly deflected, and a few, very, very few, but not zero, will have a large angle deflection. Large angle, larger than what? Larger than 90 degrees, right? Large angle deflection. So there are 3 observations here, and we have to come up with 3 deductions. Okay, 3 deductions. So the 3 deductions is, it is very likely that the nucleus is very, very small. So since it's very, very small, there's a lot of space for the alpha particles to pass through. Okay? Has anyone seen physically the nucleus of an atom before? Has anyone looked at the nucleus of an atom before? No, right? Not even him. Okay? Right? He can't even get the team right to win. Okay? So there's no way for you to view, right, the size of the nucleus inside an atom. Okay, so these are actually deductions. We deduce that the nucleus is very, very small, right? So this will help us explain why the alpha particle can pass straight through without deflecting. Okay, nobody has seen it, but from this experiment we infer that the nucleus is probably very small, right? Therefore alpha particles can pass straight through. Okay, the next one we infer, the next one will be some alpha particles, right, will be deflected like this, right? Will be deflected like this. Okay, some of them will deflect like this. And we come up with this conclusion that, right, we come up with the conclusion that the alpha particle, we know that it's a +2 charge. We know that it's positively charged. Okay, right? So since there's some deflection, right? We can now assume that the nucleus is also positively charged. Not assume lah, infer there's positively charged. Okay? Right. Some people may ask, what if it's just a normal collision? You know, like you take two billiard balls, right? If one the cue ball hits the other one, right, like this, it will deflect what? Right? It will deflect. Why is it not that? How did we come to the conclusion that it's a plus? Okay, so the idea here is the chances of a head-on collision between the alpha and the nucleus is very, very small, right? Way smaller than what we expect. So if we are getting some deflection, we can assume that, right? We can assume that the alpha particle, as it approaches a nucleus, as it approaches, even if it's at a distance away, right? As it approaches, it will get deflected like that. You understand? This is repulsion, right? So we infer, that the nucleus is positively charged. Can? Right? That's the second one. The third one is, in the very rare event of a head-on collision by the alpha particle onto the nucleus, which happens to be very, very small, 1 in 8,000 chance of this happening, right? You will get a large angle deflection like this, almost like a U-turn, or maybe even bounce backwards like this, okay? 1 in 8,000 have large angle deflection, right? So what does this tell us? It tells us that, number one, it's very rare to have a head-on collision. Number two, if it does have a head-on collision, the alpha particle is the one that gets bounced back. What does this tell you about the gold nucleus? Huge. The gold nucleus is very big, right? No, sorry, not very big. It's very small, right? It's very massive. So it's very small and it's very massive. So we understand that this gold nucleus is what? It's very dense, right? Yes. It's very massive actually. Yeah. Very massive. Yeah, very massive. So yeah, I mean it's not very big compared to the alpha particle. The alpha particle is 4. Gold is about, what's gold mass number? I mean this one you all have the memorized. How is that? What's gold's mass number? What's gold's mass number? What's the mass number of gold? AU what? 197. So 4 versus 197. Okay lah, it's like 50 times bigger, right? Yeah. Yeah, I think you can say massive, right, is better. Big, I don't think so, because if you calculate the volume, right, because if we say big, right, we are referring to volume, so it's better to say massive, right? It is massive. It's 50 times more massive, right? So the alpha particle will actually hit the gold nucleus and then it will just bounce off like that. Okay, so listen up. If you get a question like this, right, regarding the goal for experiment, 3 observations, 3 deductions. Okay? Can all right. So I just want you to understand this, okay? Right? Maybe I started off a bit rough here. I just want you to understand, prior to this experiment, right? Before this experiment, they had no idea what the correct model of an atom is. They had no idea. They had a previous model. I'll explain that previous model to you in just a while. But basically, before this experiment, they had no idea. Okay? So whatever you learn in secondary 1 and 2, the structure of an atom, small nucleus, big atomic electron shell, right? That model came from this experiment. It was not something that was ever seen before. It was after this experiment, after these 3 results, right? 1, 2, 3, Rutherford and company decided that, hey, you know what? The model of the atom should be something like that, where the nucleus is small but the atom is big, right? In order to help explain all these three things. That's why we call it a model of the atom. It's a model. It's not something that anyone has actually seen before, but it's the best working model up to date. And nobody has been able to disprove this model. So this model sticks on forever. Small nucleus, big electron shell. How much difference? How big of a difference is it? Right? I'll give you an analogy. If I take one atom and I blow it up to the size of this room, that means the walls are the electron shells. Okay? The walls, right? The walls are electron shells. The nucleus is a grain of sand right in the middle here. Grain of sand. You take one speck of sand like this, that's how big the nucleus is compared to the rest of the entire atomic size. Yeah, it's that. If you blew it up to the size of a stadium, right? Then the nucleus is the size of a cricket ball in the middle, right? Cricket ball. I mean baseball whatever. I mean yeah. Okay, yeah, that's small. Tennis ball, right? In the middle of the entire stadium. That's how big a difference there is. So when you say like, oh, there's a lot of space between the nuclei, actually there's a lot of space. There's a lot of space. Imagine two stadiums next to each other. Imagine the tennis ball in the middle of the one stadium and the tennis ball in the middle of another stadium. How much space is in between? A lot of space, right? A lot of space. So that's why a lot of the alpha particles just pass through undetected. Okay, so we come up with that model because of this. Okay, so if you get a question for this, they ask you what's the purpose of this experiment or what were the results of this experiment. We infer three things: this, and this. And a lot of space between the nuclei, positively charged, and very massive, dense. Okay, very massive and dense nuclei. Okay.
Point number two, you say that
Yeah.
repulsion between the nuclei and the alpha particle.
No. There's repulsion between the alpha particle and the gold nuclei. Yeah. This gold nuclei, I mean, they are so far away. They're not. I mean, in context, they are not actually repelling each other. Yeah. Okay. They are still within the nucleus. Okay. So there you go. This will be for this experiment, right? I'm not going to dwell on this now. All right. Let's talk about nuclear physics. Okay. Nuclear physics. Oh, hold on. Wait. Hold on. I always like to do this. Back in quantum physics, right? What do? We did this thing called electron energy levels, right? Electron energy levels. You remember us doing that? Electron energy levels, guys. Electron energy levels. Xavier, the correction tape is none of your business, right? Electron energy levels. Okay. What was it also known as? What's the other name for electron energy levels? I gave you guys another name for it. It's also known as, I mean, it's a bit obscure, but if you remember, that's great. If you don't, never mind. It's also known as atomic energy levels. The electron energy levels was also known as atomic energy levels. But why? So when we look at the atom, right, what's the first thing that we see? That the electron shell, right? So the electron energy levels is the atomic energy levels. But what are we doing in this chapter? Nuclear physics. We are doing the physics of the nucleus. So from this point onwards, right, we don't care about the electron anymore. We only care about the nucleus. And what's inside the nucleus?
Proton.
Collectively, what are protons and neutrons called? Collective name. Proton, neutrons are referred to as nucleons. Nucleon, proton, neutron, right? Okay, nucleons. Okay, this is one nucleus. What is one nucleus? What's the plural of nucleus? Nuclei. Sorry, a bit of like, physics English 101. Okay, nucleus, nuclei plural. Okay, there's something that I can't understand myself. I never really sat down to understand. If you can tell me, if you can correct me, that's great, right? I don't know what's a nucleide. I get confused by this. I don't know when to use nucleide. I know nucleus is one, nuclei is many, but I don't know what nucleide is, and we use it all the time. Like I just feel like it doesn't really matter because like all the answers I give is like, nuclei. Yeah, like if someone's googling, right, what's the difference between nuclei and nucleide? No, as in she's. So is that what's the difference? Sorry. I never really sat down to figure this out. What does it say? Eh? Okay, maybe I think okay. So this is a nucleus, right? This is a nucleus. Plural is nuclei. Okay, and nuclei is such a generic term that it can be for any kind of nuclei, be it nitrogen, oxygen, or whatever nuclei. Nuclei will be when you are trying to specify which one is the thing they are talking about for the reaction. I think that's I mean, according to specific, right? You say specific number of protons and neutrons, right? Yeah. So I mean, in a way, nuclei is a more specific term. Nuclei is more generic term. Okay, I think according to what she said, is that's probably the case. I don't know. I need to sit down and figure this out. All right, you're good with the element number. I think some of you went through this one, right? Just to point out to you, A is your mass number, it's your nucleon number. It's basically the literal number of protons and neutrons inside. Okay, right? Chemistry, chlorine is what? 35.5. Okay, right? We don't have point something for physics. You can't have a half a proton, right, or half a neutron. Okay, so we have to have whole numbers. So for physics, right, when we talk about chlorine, which one are you talking about? Are you talking about the chlorine 35 or are you talking about the chlorine 37? Right, so you got to be specific. No, it might be either or, right? So there's no such thing as 35.5 for physics. Okay, so this is not your relative mass number. This is your absolute mass number. It must be an integer value. Okay, so mass number is A on top, Z below, right? Like Amazon, A to Z. You all know the Amazon logo? There's an arrow at the bottom, A to Z. We ship everything from A to Z. Get it? Amazon. Anyway, right? So A to Z here, right? The thing is, Z is your proton number, right? It's your proton number, otherwise also known as your atomic number. This is the part that got confusing. A on top stands for mass number, but Z at the bottom below stands for atomic number. Right? Great. Okay. Now I just confused you. Right? Try to figure it out on your own. All right. So atomic number is the bottom. So proton number is the identity number. Okay. Like for example, 2 protons. Which element is that? 2 protons. Helium. Good. 3 protons. Lithium. 6 protons. 6 protons. Which element has 6 protons? Carbon. Yeah. Carbon 12. Oh. What? Sodium is 11. Yeah, sodium 11 to 23, right? Yeah. Okay, you understand this, huh? So the proton number is the identity number of the element. If you can change the proton number, you are literally changing the entire element. Right? If you change from 6 protons to 7 protons, so let's say you have another extra proton, right? It becomes nitrogen. You get what I'm saying? Okay, good. Now, this is completely, the next thing I'm going to tell you in the next 5 minutes, completely not in syllabus, but doesn't mean that you switch off, huh? Right? I just want you to, no need 5 minutes, 3 minutes only, okay? 3 minutes, listen up very closely, right? Has anyone explained to you before why the protons are stuck to each other there? What? Where's the minus? Bro, where's your minus? Day, where's your minus is on the outside. Your minus is on the outside. So nobody even in the school lectures. All right. So I just taught this to my O-level class. All right. So basically, I have a batch of students now that will go out into the world and help explain why protons can get stuck to each other inside a nucleus. But you guys don't know yet. So now I explain to you, okay? Okay. So in the nucleus, there are other things happening. So it's not just like protons and neutrons share, like, being friends and then just shaking hands like this. Okay? No, in fact, inside the nucleus, right, the protons are desperately trying to repel each other. All right, keyword, desperately trying to repel each other. Okay, how many protons are inside this example here? This one. Wait, hang on. No, be very careful when you say binding energy. What's that? 7 protons, there's 7 protons. Guys, if you have 7 protons, right? If you have 7 protons, every 1 proton is experiencing 6 repulsions. You get what I'm saying? So if all of them are repelling each other, if all the protons are repelling each other, what's holding them together? That means there must be a reason why the nucleus is stuck like this, right? If not, they would have been flying off already. Okay? So there is something that your teachers didn't tell you. I'm going to have to let you know, right? It's called strong force. There's this concept called nuclear strong force, right? A nuclear strong force. Heard of it? Your teacher said before. Nuclear strong. No, never said before. Okay, a bit worrying. Your teacher at least got say nuclear strong force. Nuclear strong force. No. Okay, let me tell you this. Okay, it's a nuclear strong force, right? Okay, there is this force inside, but it's not in your syllabus at all. It's just that I want you to know that there's this force. This is called the nuclear strong force. It's kind of like glue. Nuclear strong force. Right? There's this thing called nuclear strong force. You understand this? Right? It's kind of like glue. It's like glue. How does glue work? How does glue work? You take something, you apply glue, then the other thing you must put it together, right? Okay, that's the whole idea. Nuclear strong force is extremely short range. That means you can't apply glue on one thing, right, and then expect it to attract the other thing from far away. So if you want to glue things together, you got to really make them close to each other. You understand what I'm saying? Okay, so that's a property of the nuclear strong force. In case you ever go out into the world, walk outside into the world, and they meet international people, and international people ask you, oh, so you studied nuclear physics when you're in JC? Cool, right? Do you know why do the protons not split apart in the nucleus? And you stand there. Nobody told me this before, no. Okay, so now you know. Okay, so now you know, right? There's this thing called nuclear strong force, right? And nuclear strong force acts like glue. Okay, the reason why I keep saying glue is because there is something that goes on inside. There's this thing called the gluon. I'm not making this up, okay? All right, there's this thing called the gluon that literally glues them together, right? Kind of like they have a strong force that binds them together. Okay, you get what I'm saying? Okay, good. What you also should understand is, hey, if there's this thing called a strong force, if there's this such a thing as a strong force, right? Do you think you can ever get a nucleus that's just purely made out of protons? How about I have like pure protons like this? How about that? They can glue each other, what? Can I make a nucleus that's like this? Can or not? Cannot. Why cannot? Because the repulsion here for this case is way too strong for the amount of glue force, right? Gluing force that they have, right? The strong force that they have. So this kind of nucleus will definitely break apart, right? So in order to stabilize this nucleus, what do you need? The neutrons. Neutrons are what? What charge? Neutral, right? They don't take part in any repulsion. They are not attracting either, right? But they help to increase the number of strong forces in the nucleus. So with more strong forces, the nucleus will become stable. Will become stable, right? So the reason why you always have a mix of protons and neutrons is because it helps to stabilize your nucleus. Okay, just a heads up, because that's a bit later. What happens if you have too many What happens if you have too many neutrons? Unstable. What happens if you have too few neutrons? Unstable also. Okay, so it's not up to you to judge whether or not it's unstable or stable. Like, if I show you a nucleus and then you say, is it unstable or stable? It's not up for you to judge. But the thing is, if it's unstable or stable, it will decay. If it's unstable, it will decay, sorry. Right? It will decay. But decay is later. I haven't done decay yet. Right? I'm just going to give you an understanding of this thing here. So no matter what's holding these guys together is really the strong force. That's why protons don't fly away from each other. Okay? Now you guys are ready to walk into the world to tell people that you are learning nuclear physics. Do you realize that all your peers who have never heard of this nuclear strong force before, right? They go out there, right? They cannot explain this either. And you've been doing chemistry for like what? Sec 1 to Sec 4, J1 and J2. Nobody knows how to explain why the protons don't fly away from each other in the nucleus. I don't get that. How come it's not part of the core syllabus? It's one of the most fundamental things, right? We know positive charges repel each other, right? So why are nuclei stuck to, like, stuck in a ball like that? Yeah, they should just teach this strong force. I don't get it. I find it very strange. Just add it into chemistry or something like that. I don't know. Just put it there somewhere, right? But anyway, now you know. Okay, now you know. Correct. Hydrogen is lonely. I'm so lonely, right? There's nothing to bind to, which later on you will understand. Okay? All right. So start with hydrogen first. Let's start with hydrogen, huh? All right. So we go to this page here. Let's start with hydrogen. Okay. Now, this one I need you all to know, because especially for those who don't take chem, right? You need to know this. What is a hydrogen atom made of? One pro. Where did the neutron come from? Okay, so hydrogen on its own is just one proton and one electron. If you lose an electron, what does it become? Just a single proton, right? Which is known as the hydrogen ion. Yeah. Right? You understand this, right? It's just H plus, right? Okay, but this is not chemistry lesson, huh? So this is hydrogen. What happens if I have a neutron attached to it? What is this? No. Huh? No, neutron. What? Neutron. Eh? Neutron useless. Guys, same number of protons, different number of neutrons. Isotope. It's an isotope. Okay, it's an isotope of hydrogen. It's still hydrogen. Please, especially for those who don't take chem, you have to know this for 7 and 12. Right? Both chapters writes on this. Okay. Your proton number is your identity number of the element. If it's one proton, it is hydrogen. If it's two protons, it is helium. If it's three protons, it is lithium. Right? Four protons, I don't know. I only know up to okay, I don't teach chem. Right? So proton is the identity number. You change the proton number, you change the element. So if this is one proton, right, and you add on one neutron, that's still hydrogen. But there's a special name to this thing. It's called deuterium. Deuterium. Okay? Deuterium. So if you see deuterium, whoa, big word, it's just a hydrogen isotope. Right? It's a proton plus a neutron. Okay? Right? Don't reject it just because you really cannot stand chem, right? I don't know what trauma you might have experienced before back in secondary school. Was it really bad? No, I know, but were you scared of it or what? Did they scare you out of it or what? Okay, all right, that's very strange, but okay. Okay, this deuterium. Now what happens if I go and add on one more neutron? Yeah, it's tritium. Good, tritium. Anyone watch the original Spider-Man movie? The one with Tobey Maguire? What? What's that? Is that the first Spider-Man game? No Man's Sky. No Man's Sky. That's an open world game, right? Isn't it? Yeah. That's a super. You play that one. Yeah. That's damn boring. Yeah. It's like endless. Okay. Oh yeah, that's right. Right, tritium. Okay. Yeah. The first Spider-Man movie, the Dr. Octavius was trying to steal some tritium from some science lab or something like that. Anyway, that's tritium. Okay. So just to give you an idea, because you will see this hydrogen, deuterium, tritium a lot of times, right, as you go along 7 and 12, right? So just to introduce this to you. All the other classes are asking me, do I need to know this? The answer is yes. Yeah, you need to know this, okay? All right. Go back to the original normal hydrogen. How many electrons does it have? Because we're doing atomic physics, right? We're doing the electron. So how many electrons? One electron, okay? Right? When the atom is cold, when it's cold, right, what's the electron doing? Hey, it's not stop moving, It's not that it stop moving, It's orbiting still, right? So it's still orbiting like this, right? It's still going around like this, right? But it's at the slowest and it's at the lowest state, right? Called the ground state. Ground state, right? It's called the ground state, okay? So the lowest and the slowest ground state, okay? Please look at this. The electron is here. You see this thing here? Yes. Yeah, that's the electron. It's at the ground state. When it's at the ground state, the n is equals to, yeah, n equals to, what's that? Yeah, it's just arbitrary number, n. Yeah, n is equals to 1, not 0. Not 0. Right? In Singapore, our ground floor is always 1F, right? Okay? Not like other countries. Ground floor is GF. Right or not? Okay? So anyway, Singapore 1, okay, so first floor is here. Then second floor, third floor, fourth floor, infinity. Right? So I show you a couple of things. A few other things. Notice how the energy levels. So these are the energy levels where the electron can go up to. Right? Notice this 1, 2, 3, 4, then infinity. What happened to 5, 6, 7, 8, 9, 10? They're in between. They're in between, but they're so close to each other that you can't see it. Right? Very good. Yeah. So it's all here. But so most of the questions, 95% of the questions for this chapter is only up to level 4. Okay? Right? Just think of that. Right? Look at the ground state now. Look at the ground state of this electron now. Okay? There's an energy value associated with the ground state. Now, which element is this again? Hydrogen. What? Deuterium? Hydrogen. There's no neutron in this thing. Hydrogen. This hydrogen. Okay? It's hydrogen. Just normal hydrogen. Right? This is the energy value given to this electron. Right? This energy represents what? What does it have? What does it represent? What kind of energy does the electron have? Ke. And what kind of Pe? Not GPE, because gravitational potential energy for electron and proton is very, very small. EPE, what's EPE? Electric potential energy. Where do you learn that? When do you learn that? Topic 10. Topic 10, potential energy. You learned it in topic 10. During the consult, I thought I went through this. You were there, right? During the consult, calculating the EPE and GPE sum. The day before the test, I did a test consult. Oh, can you text me?
Okay.
Send the KE and GPE of electron to the rest. Yeah, I'll send the video also. Yeah, KE and EPE, sorry. Yeah, KE and EPE. So even though you sum up the KE and you sum up the EPE, what's the value of the total energy of the electron? It's negative 13.6. Okay? What's EV? It stands for electron volts. What kind of unit is that? Yeah, but what kind of unit is EV? You should have known this from topic 5. Yeah, it's a version of energy, but it's the non-SI unit of for energy. What's the SI unit of energy? Joules, right? Like what you said. So EV is just a simpler value when you deal with electrons. Okay, so EV is a unit of EV is a unit of what? Energy. Is it SI?
No.
It's non-SI, but it's just a simpler version of it, right? Okay, so EV is a unit of energy. So it is energy. You can convert it to joules if you want to, right? But it's negative 13.60 EVs, right? When the electron is here. Question, why negative? What's the significance of having total energy as negative? Good, it's attracted to what? To what thing? What's inside the nucleus? The proton. There's only one proton. The fact that the electron is still attracted to the proton, therefore the total energy is negative. That's why it's negative 13.6. It means it's still bound to the electric field of the proton. You got this? Yeah, you have to convert. You have to know how to convert. This is from topic 5, so you need to know this, okay? I can show it to you now. You need to memorize this. All right? 1 EV is 1.6 times 10 to the power minus 19 joules. But does this number look familiar to you? This is what? What is this? What's this number? This is the charge of 1 electron. So 1 electron volt literally is 1 electron times 1 volt, because 1 electron volt, 1 E times 1 V. Therefore, in joules is 1.6 times 10 to the power minus 19 joules. Right? This is from topic 5. You should have known this from topic 5. So doesn't matter. You can memorize it now. Just remember that you need to know this. Okay. What? Who said something? I heard something. Was it? I thought it was Sam, you know.
Yeah, something going wrong.
We sabo them. Sounds like, why would any of you are damn random lah. Okay, guys, question what if I gave this electron 13.6 eV on the dot, like I supply it with energy, I give it, like since it's negative 13.6, right? It's trapped with the proton, right? I give it 13.6 eV of energy, like you don't know how yet, but I give it, what will happen? Not just fly away. I mean, you're not wrong, but exactly what happens? It will jump to infinity. It will jump to infinity. If I give it, right, if I plus 13.6 EVs of energy, right, if I supply with energy, so that its total energy becomes zero, this electron will go to infinity. What does this mean? When the electron goes to infinity, what does that mean? It's not bound anymore. So what happens to the atom? It becomes... Actually, I should stop asking you. You cannot answer me these questions one because you have no idea how to answer. Yeah, exactly. Jianxiang, you take chem, right? Yeah, what happens when the atom loses the electron? What's that process called? Ionization. This ionization, this is your first ionization energy for hydrogen. Huh? Don't worry, none of your business. But I'm just trying to draw the relationship for those who take chem. Okay, right? But in physics, right, we don't want to ionize the electron. We want to torture it a bit. We want the electron to jump up and down within the levels. Let it go up, let it come down. Let it go up, let it come down. We're never gonna let it go. Right? Never gonna give you up. Never gonna let you down. All right, but so we don't really care about ionizing the electron. So but it's just a thing, right? It's a thing that if you give it that amount of energy, it will escape, right? But we're just gonna let the electron go up and down the levels. Okay, when you go up the level, it's called excitation. And down here the value. Yeah, it's written here already. When you go up the levels, it's called excitation, right? But in order to do that, what must the electron do? Must absorb energy. Okay, I'm going to use the word absorb. When the electron de-excites, means that means when it's at a high level and then it drops back down, then we call it de-excitation, right? When the electron de-excites, what must the electron do? Emit energy. Okay, good. So here's the thing, right? So at a cold state, right, when you do provide energy to the electron, not sufficient for it to escape, but sufficient for it to jump to another level, right? The question is, what does it do next after being excited? Like, what happens when it goes up to the next level or goes to this level? What does it do next? Immediately, it will de-excite. So basically, it gets excited, right? It will just go back down. You go to third level, also come back down. Go up, go down. Why? Quantum mechanics. All right, you don't need to explain why. You just need to know that it happens. Okay, you just need to know that it happens. It doesn't stay. It doesn't stay at the excited state. It will quickly de-excite. Okay, in short terms, unstable.
So when it goes up, it has to come.
Yeah, yeah. So try not to draw any parallels to 1s2, 2s2 for those who do chem. Right? Don't need to. Right? For physics, we just treat the electron levels like the shells. Right? Just the normal shells that we learned long ago. Right? So you just remember that it goes up, goes up, goes up like this. Okay? Now this is really a lot of chem, which you should have picked up from Sec 3 and Sec 4, but you didn't. So you just have to think of it in a physics term. Because don't forget, chem is really applied physics. No, you don't have to memorize, but you need to understand this. These values here are specific for hydrogen. The example that I'm using here is specific for hydrogen. This doesn't apply to all the other elements. Different elements will have different energy levels. These values here that you see here are specific for hydrogen only. If it's mercury, if it's sodium, if it's helium, they have their own levels, right? And the question may give you other levels. Can? All right. Now I want you all to flip to topic 12. Data booklet, topic 12. Data booklet, topic 12. Look for this number, 13.6. I'm very sure you can find it there. Topic 12. Right, you see it there, right? Yeah, okay. So you should understand that equation there is meant only for, very good, hydrogen only. That equation is only meant for hydrogen. right? Not for any other elements, right? Because this is only specific hydrogen. You don't have to memorize anything, okay? You don't have to memorize anything, but here's the thing, at some point in topic 12, you will be expected to use that equation there in topic 12 to go and calculate the energy levels here. So even though I said don't memorize these values, you have to work them out. But it's very easy. Can you see the equation there? What's the full equation? E equals to negative 13.6 over n squared. What's n over there in the equation? Right here, this n. So what happens when you take 1 squared? Yeah, the ground state is negative 13.6. EV. Do you see the units at the back of the unit, the equation there? EV, right? Okay, can you try 2? Can you try 2 and see whether you get this number 3.4? Right? So 13.6 divided by 2 squared. Yeah, you get it, right? So these values here correspond to the equation over there. Okay? But only for hydrogen. Only for hydrogen. Okay? Yes, only for hydrogen. I'm teaching you all the tricks of the trade. Like, you know, it's kind of like this will help you catch some of the questions, the weird ones in the exams next time. Okay. Now, let's do some math very quickly. So in order for this electron to jump up to the next level, how much energy does it need? What's that? Wow, quick math, huh? Someone? 10.2 EV, right? 10.2 EV. Next question, can the electron jump halfway? Cannot. Electrons cannot jump halfway. It's either you go there or you don't, right or die? Did I use it correctly? Okay. Anyway, so if you want, you can jump up to the 3rd level, you can jump up to the 4th level, right? Or if you want, you can jump up to the second to 3rd, 3rd to 4th. Yeah, it will. You're right. So what happens is, once it's here, right, it has a choice. Or rather, depending on the situation, it could either jump further up if it has the correct amount of energy, or is exposed to the correct amount of energy, it can jump up, or it will come back down. So, you know, like nobody knows. Yeah, correct. If there's the correct amount of energy for it to go up, it will go up, or it may come back down, right? There's like a 50-50 chance. Oh. Okay, hang on. So the thing is, a lot of students will ask this question. So which is the most likely path, or most likely step that you will do next? Would it excite or would it de-excite? Even with the correct amount of energy, right? That for it to jump up to this one, would it do this or would it de-excite? The answer is it will do both. Okay, the reason is this. This is only one atom. For all the experiments that we do, it's always a cloud of hydrogen atoms, a cloud of hydrogen atoms. And in a cloud of hydrogen atoms, how many atoms are there? Gajillions. Yeah, gajillions. 10 to the power of 26. If it's 1 mole, right? Gajillions, many atoms, many atoms. You understand this? So the chance of any of them going up or coming back down, 50-50. There's equal chance. So all pathways are possible. So in this chapter, yes, especially later on, I'll show you some pathways of how they excite and how they de-excite, right? It is not a question of what will happen. It is more of an understanding that all of them will happen. Can? Okay. Can? It will all happen. It will happen. Don't go and say that, oh, what if it decides to go up instead of going down? No, it will all happen. It all happens. Can? Okay. Because this is something that's not explicitly told you. Right? Yeah. Yeah, it just wouldn't stay there. Yeah, you're right. It just wouldn't stay there. Quantum mechanics, probability, statistics. Okay, so let's not go there. But the statistics is such that there's so many atoms that by random chance it will all happen. Basically, anything is possible. Yes. No. But that's if they give you the value for the ground state. Okay, no. Sorry, I would say no, because that equation was derived based on hydrogen. It doesn't work for any other elements. Yeah. Wow, that's a good question. Yes, it does. Yeah, tritium. Yeah, that's a good question. It works. Yes, but they haven't. I've never seen a question like that before. Yeah, but he's not wrong. Yeah, you just can't use it for helium, for example. Yeah. Okay, Ken. Right. Now the question is, how does the electron absorb the energy? Huh? No, how? How does it? Where does it get the energy from? This one you all should learn in chem already. Yeah, light. You're right, light. It absorbs it from light. So what we're gonna do is, in your mind, just imagine this. There's a cloud of gas, and we're gonna shine light on it. Okay, we're gonna shine light on it, and the electrons on the atoms will absorb the light, and then they will excite and de-excite. They will both do both. Can? Okay. So the question is why? How come light can cause the electron to excite? If I shine light on you, would you be excited? No. That's strange, Tina. Okay, and the reason is, okay, light can be thought of as a stream of photons. Photons, okay. So now the thing is this: your chem teachers explain photons. Did they even mention photons during the spectra part of chem? They just mentioned light, is it? You can't remember? You? Do you hear the word photons before? Okay, so here's the thing, this is classical physics versus modern physics. Classical physics, light is known as a wave. Modern physics, light is known as both a wave and particles. The particle is photon. So when I shine a laser like this on my hand like that, right? Okay, when I shine a laser on my hand like this, right, it's thought of as one stream of photons. Right, just like one line of photons going towards my hands. Okay, when we talk about photons, we don't talk about waves. When we talk about waves, we don't talk about photons. You understand this? It's just that light can behave both, but not at the same time. Right? The idea is that the different experiments that you conduct, light can behave like a wave. Then there's another experiment that you conduct, light can behave like a stream of particles. Can? Okay, you understand the phrasing so far, right? Okay, what are the wave experiments that you have done? What are the wave experiments that we have done so far? Double slit. What else? Single slit, diffraction grating. What else? What other wave phenomena have you done? Basically, the whole of chapter 4 and 9. Yeah, everyone hates it. Everyone hates it. You didn't join early enough. I was doing revision on that in November, December. Yeah. Yeah, I know it's a terrible chapter. I will do the revision for that in this year, August. Unless they decide to test everything in July, then I have to do it in June. Well, what else? What else do you do so what other wave experiments have you done? You have done superposition, standing waves, right? Single slit, double slit, all of that, diffraction grating, thin film interference, interference superposition, all that. All those are wave phenomena, right? Okay. But the experiments for photons in topic 7 have not been taught yet. It will be taught in topic 12. So you, Jada, will start off this quantum thing with the experiment in topic 12 first. That's why I said your sequence of chapters is like 12, 7, 12, 7, 12. Yeah. So they want to go through the experiment where we prove that light exists as photons first. I'll get there somewhere in March. Okay, we finish 7 first, then we go on to 12. But just remember this, the experiment that proves that light exists as photons, have you learned it yet? Not yet. Which chapter? Topic 12. Right now, I'm just going to force feed you that light exists as photons, and you have no choice but to accept it. Okay, so But now what I want to do is this. If they exist as streams of photons like this, right? If you think of them as photons, right? Photons is a packet of energy. Is a packet of light energy. So these are red photons and these are violet photons. Can you kind of tell me what does this suggest? Yeah, there you go. One violet photon has more energy than one red photon. He's right. And 7 and 12 are the quantum part of things, a lot of it rides on this. You're understanding that a violet photon, a single violet photon has more energy than one single red photon. But why though? Which one? Shorter wavelength? Violet has a shorter wavelength. Okay, so not technically due to wavelength, but due to frequency. Right? Violet has a higher frequency. All right, violet has like by definition is due to frequency, but of course it's inversely related to wavelength. Higher frequency lah, bro. No, per photon. Per photon. Now we're comparing per photon. Okay? So it's not about the total number of photons, right? So per photon, each photon of violet is more energy than one photon of red because the color has a higher frequency. Of the entire spectrum, which one has a higher frequency? Spectrum, the entire spectrum, the EM spectrum. Gamma has the highest frequency. Gamma photon is the most energetic. Okay? Right now we're comparing for visible light. Red, orange, blue, green, red, orange, yellow, blue, green, green, blue, indigo, violet. Right, GB? Can? Okay, okay. The equation is E equals HF. E equals to HF. Yes. What does H stand for? What? H is known as Planck's constant. Planck's constant, nobody cares. Right? The Caucasian teacher in SGI will be quite particular about it. Okay, but this I call it Planck's constant and multiplied by frequency of what? The light, right? Okay, so I want you to do this for 7 and 12, right? Always think of frequency with regards to the color. Low frequency, red. High frequency, violet, blue. Okay? Frequency, okay. So, but it does turn out that it is inversely related to the wavelength, so you can rewrite this equation as hc over lambda. Okay? Right? So the wavelength is inversely related. But the wavelength doesn't refer to the size. So some people say that, how come I draw the violet photon so big? Right? But then the wavelength is actually very short. The wavelength has nothing to do with the physical attribute of the photon. Right? This is just a diagram to show only. This is not a real thing. This is just an analogy. You know? TOK? Analogy. Why are analogies useful? Huh? No, you don't have to draw. I'm just trying to help you visualize, form an image only. Right? Just to help you remember that violet is more energy. Can? Per photon. Okay, what's C? Speed of light in vacuum. Must always quote in vacuum. C is always speed of light in vacuum because vacuum has the letter C in it. Okay. What? Char siu also vacuum? That's the first thing you think of is char siu, dude. What the hell? You gotta tell a roast duck, right? Okay, so E equals to HF, right? E equals hc over lambda, right? Every photon has a different color, has a different energy. How many colors are there? It's not 7. It's not 7. Okay, I know it's Roy G. Biff, but there are millions of shades and hues in between. Okay, there's millions of shades and hues in between. So it's basically all the kinds of photons. So now the question will be this. What is white light? Every single photon that you can imagine, right, exists in white light. Every single one of them. Okay? You know Jace? JACE, year 5. Oh, okay. Yeah, he's coming in. He's from SOTA too. I sent this picture out the other day. The one with the party symbols. Look like party colors. This one. Yeah. What's white light made of? This. There you go. So this is just to give you an idea of what white light is, right? There's red photons, all the kinds of photons. Can? Okay. Number one, and the most important thing, right, at this point in time, do not confuse the photon and the electron. At some point, some people will be confused. Yes. Okay, where's the electron? On the atom. Where's the photon? Is the light coming in? So you have an atom and the light is coming in like this, right? So what does the electron absorb? It absorbs the photon. Yeah, what's a photon? Packet of energy, light energy. Okay, so it absorbs the photon itself is already absorbing the energy, right? The photon itself is the energy. Okay, and the rule is this: you can only absorb one per transition. You can only absorb one photon for each transition, for each excitation. That means you cannot sit at the ground state, right? And then absorb like 3, 4, 5 photons, and then you jump to the next level. You can't do that. You can only absorb one at a time, one per transition. So if you absorb one, right, and it allows you to jump to the next level, right, and the next level you can absorb another one, smaller energy, right? You can absorb another one if you want to jump up to the next level, if you want, if you can, if there's availability. You understand this? So the rule is one photon at a time. And what excites? Does a photon excite? No. What's the thing that excites? The electron. So do not confuse a photon and electron. Yes, two different photons. Two different photons. Yeah, so you're right. All right. So for it to jump. Okay. So okay, one more time, just to re-emphasize this, because this is the part where a lot of students get confused. This equation E equals HF is for the photon. It is the energy that the electron will absorb, but this is not to calculate the electron's energy. This equation doesn't help you calculate electron energy. This equation helps you calculate the photon. So only for photon, right? So make sure that this equation is photon. F for photon. E equals to HF. F for photon, right? So, or you want the E equals to, right? Then you can write photon. Okay? Right? There you go. Right? Bad spelling, right? Because physics is important. Okay, there you go. Right. So just remember that this is only for the photon. Okay, good. So just take note of this, right? So electron only absorbs one photon at a time. Okay. So let's talk about absorption in the next page. Let's talk about absorption. So in this picture here, there's an atom here, right? There's an atom here, and the light is coming in. Light is coming in, and some photons will be absorbed for the electron to excite. You understand this? Okay. So knowing that the electron only absorbs one photon to excite, the question is, how much does it need to go to the first level again? First level, first excitation, 10.2 eV, right? What that means is that in order for this electron to jump to this level, the photon, that one single photon, must have exactly this amount of energy. It cannot be less, cannot be more. It cannot be more. It cannot be more. It must be exact. Because if you give it more than 10.2, right, then that would mean that would suggest that it will jump to the level above. It doesn't hang there, right? It has to be the exact level. Yeah, it wouldn't. No, what? Sorry. Let's say 10.5 eV. Okay. Let's say I give it a 10.5 eV photon. Let's say it's a 10.5 eV, right? Like this. The question is, will the electron absorb this photon? The answer is no. Why? Because it cannot absorb anything that has more than what it needs for the excitation. I mean, what's to the next level? How much is it to the next level? This is plus 10.2 eV. What's the other one? Plus 12.09 eV. Correct, right? Yeah. Anything in between from 10.2 to 12.09, right? The photons won't be absorbed by the electron. Why? Quantum mechanics. None of your business. You just need to know how it works. Quantum mechanics. There's no human. What? Ant-Man. What? Yeah, it must be exactly 10.2, right? The photon that's being absorbed by the electron, because the quantum mechanics states that, okay, we have to follow the rules, right? What are the rules? It can only jump to this level, and it cannot have excess energy because, you know, it's not like it can go to above here or it can shed away the energy. It can't. Mm-hmm. Both will happen, right? Because there's so many instances, both of them will happen. Yeah, but what did we say about the cloud hydrogen atom? So it's not that this electron is accepting both. This electrons accept 10.2, the other guy is accepting 12.09, and it's just like evens out everywhere. So all of them will happen at the same time. But that's a good question, right? That's a good question because like it really makes you think that actually yeah, it only can it all will happen. Huh? No, hydrogen only has one electron, right? Hydrogen only has one electron. That's why we only show one electron here. Yeah. Hmm? No, it doesn't absorb both. Sorry, what's the question again? So you mean that if I have a 10.2 EV and there's a 12.09 EV, right? Okay, coming in, right? Okay, this particular hydrogen atom will choose one of them. Like it will just be a random chance of absorbing one of them, right? The other one will not be absorbed. This particular hydrogen atom will excite to this level, right? But there's so many other gajillion hydrogen atoms, so the chances of them exciting by the 12.09 is also possible. So we'll treat all paths are possible. Yes, will absorb the 12.09 or other 10.2s because white light is just all the photons and there's many copies of it, right? Yeah, there's many copies of the thing. Okay, but my point is that you will realize that means that only some specific photons are absorbed because it's so specific. It's so the requirement is so stringent. It must be the exact amount of energy for it to jump up to the next level that only some photons are absorbed. Not all of the millions of photons of the different photons that you have. Only a select few will be absorbed. All photons of the same color will have the same energy. Yeah, only certain colors will be absorbed. Yes, you're right. That's a good one also, right? So only certain colors will be absorbed. Okay, but when we say color, are we talking about the whole range of like orange photons? No, right? We're talking about a specific orange shade and orange hue, right? Yeah. So that will be, yeah, that if that one is absorbed, all the other hydrogen atoms will also absorb it. Basically, that color will be absorbed, gone. Yeah, right? It'll be gone. But like I said again, so you should understand that only a few, right? Only a few will be absorbed. Not all, right? Only a few will be absorbed. Correct? And how many colors do we have? Millions, right? There are millions of colors, right? In fact, right, if most of the questions only deal up to level 4, right? Only deal up to level 4, right? Let's draw all the possible pathways to level 4. You could do some intermediary excitation here. I'll tell you this, most teachers won't show you this. They'll tell you that, they may even tell you that it's not possible, right? I've done my research, it is possible. If you have the correct amount of, if the photon has the correct amount of energy coming in, it can excite. If there isn't, then it won't, right? If there isn't, then it won't. But I'm just telling you that it is possible. Sorry, what? Huh? What? It's only no, hang on, hang on. So what are all the possible pathways to get to level 4? Right? You can jump straight up. You can jump up to 3, then from 3 to 4. You can jump to 2, then 2 to 4. Any other possible pathways? Any possible? No, right? Up to level 4 don't have, right? Okay, but my question is this: how many unique photons will be absorbed in all these 4 possible pathways? How many unique photons will be absorbed? Very fast, 6. Right? Do you see 6 unique transition values?
Yes.
Right? You see 6, huh? This one, 1, 2, 3, 4, 5, and 6. Okay? There's some math to it. It's called 4C2. Okay? 4C2. Right? 4 choose 2. 4 levels, you choose 2. One start, one end. How many combinations do you have? 6. 6 unique combinations. Because this is useful only because when they ask you for 5 levels, How many unique photons? You will calculate 5, choose 2, 10 unique photons. That's about it lah. They don't go anything further than that. You can draw it out and go and count the number of unique photons. Right? It's just that I'm showing you a shortcut here. Can? But no matter what, right, of the millions, guys, of the millions of photons present in white light, to excite to level 4, how many unique photons have been absorbed? 6, 6, right? 6 unique photons have been absorbed. Not just one, because all of these are possible. We are only drawing for one hydrogen, but it's basically representing all the possible pathways for all the other hydrogens, and therefore all the 6 unique photons will be absorbed. That's why you need white light, because it's to provide all the different colors. But of all the different colors for hydrogen to level 4, you only absorb 6 unique photons, 6 unique colors. You understand this? Can 6 unique colors, and that is why for the absorption spectrum, okay, for the absorption spectrum, I'm going to end this here. For the absorption spectrum, it looks like this. This is why this is called the absorption spectrum. White light is all the colors. White light is all the colors, right? But after the photons have been absorbed, what happens? They go missing. Yeah. So these lines here represents the photons that were absorbed by the hydrogen. Is missing. Okay. So the photon energy represents the transition of the energy levels. Right. For example, maybe this is like a 10.2. Right. This one 10.2. Maybe this one is a 12.09. Yeah. Something like that. That specific one. Now, the values and this diagram are not perfect match. Okay. This is just an example. In school also they don't, in textbooks also they don't show you the exact values, right? Because it's very complicated. Somewhat in chem you learn what? The Balmer series, the Lyman series, you heard of that, right? That we don't do that in physics. We don't do that in physics. In physics it's just very straightforward. What do the black lines represent? Photons that were absorbed, right? What happened to all the other colors that were not absorbed? What happened? They just passed through the cloud. So you had a cloud of gas, right? And you shine white light on it. So some colors are being absorbed by the cloud and the rest of them pass through. That's why you can see all the other colors except for the missing ones that were absorbed. Okay? This is called the absorption spectrum.
Does that mean there's colors we can't see? Because they've been absorbed by like the stuff.
Yes, but generally, because of the presence of all the other colors, when I combine all these, it still looks white.
But it's not white.
It's off-white lah. Slightly off-white lah, but generally still white lah. Our eyes can't tell the difference.
No,
Unless you're a mantis shrimp. They can see the widest range of spectrums, all the way from infrared to UV.
I thought their only specialty is like punching as fast as possible.
Yeah lah, and they can see fast and they can punch fast lah.
Wow.
Okay, anyway, so just think about this. So in the next lesson, please remind me to go through this paragraph. I basically have not gone through the paragraph. Yeah, this is exactly the thing that you need for 3 marks in the exam question, right? Topic 7 we're talking about here. What's this? No, that's absolutely right. But what's the name to this picture? What is that? What? Wrong. Absorption spectrum. It's a hydrogen absorption spectrum. It's not specifically hydrogen. This is actually just the generic absorption spectrum. But it is an absorption spectrum. Hello. This is absorption spectrum. Okay. Right. Here's the thing. Do they print color in your exam papers? They don't, right? Okay. So here's the thing. They will ask you describe the absorption spectrum. So reverse engineer on you, right? How do you describe this? Like what you said just now. What is it? Black lines on a colored background. Yeah. Black lines on a continuous spectrum. That's how you describe it, right? Reverse Uno on you, right? I ask you this, right? Describe it in words. How does the absorption spectrum look like? Black lines on a pen. Take out a pen. Start writing stuff. Okay? Right? On a continuous spectrum. You can say continuous spectrum or you can say a colored background if you want, right? Black lines on the colored background. All right. Did I go through what do the black lines represent? Do you know how to do this from chem? Yeah, they're missing colors, but why, what does the missing colors represent? The photons that were absorbed. Absorbed to do what? Excite what? The electrons, right? So what's the deal with the black lines? They are specific, right? So specific photons were absorbed for the electrons to excite, right? What does this tell you about the energy levels of the electrons? Energy levels. They're discrete, right? Discrete. So the energy transitions are also specific. Did I go through this last week? I think I went through this last week, right? So I'll just quickly touch on that, right? That was what's described in here. So if you don't want to write all that down, it's all here, right? What's your aim? What's the aim for you for this chapter? Like, if you go to the exam, right? What is the thing that you need to be able to do? Answer a 3-mark question, right? On what does the absorption spectrum do, right? What is the absorption spectrum for? What is it meant for? It is meant as evidence, right? Evidence for discrete energy levels in an atom. Okay, but that's the absorption spectrum. So that's a recap from the last lesson, right? Then the next one you need to learn is emission, because when the electrons excite, what do they do next? After they're excited, what do electrons do once they're excited? What? Oh, okay. What would the electron do after it's been excited? No, as in like moving to higher energy levels, excitation. Once it's excited, what would it do next? It will relax. It will de-excite. Okay? And when the electron de-excite, what does it do? There you go, emit a photon. So it's basically just the opposite of absorption, right? You absorb a photon, the electron absorbs a photon to excite. Then once the electron is excited already, the electron will de-excite and emit a photon, right? You'll emit a photon, okay? Right, so there you go. So most questions will start off with the electron being at level 4 like this. How will this electron de-excite? Straight one path, go straight down to ground state. Any other pathways? Go down to 3, 3 to 1. Yeah, 3 to 2 to 1, 2 to 1. Yeah, the 3 to 1 already. Yeah, already here already, 3 to 1. Oh, 3 to 1. Okay, good. Okay. All right. Which is the preferred pathway? All are possible, right? Good. All right. So this guy is remembering what I said the last time around. So all pathways are possible. There's no such thing as a preferred pathway. All of them will happen. How many unique photons are there in these 4 pathways? 4C2. So how many is that? 6 unique photons. So when the electron is at level 4, and I ask you how many unique photons can it emit, every one of these arrows, every one of these transitions, even if it's like, from 4 to 2, that one arrow is one photon. It emits one photon. Okay?
So it was like that. N equals 5 if I choose.
Yeah, it'll be 5 choose 2. Yes, you're right. There will be 10 unique photons. What? 4C2 is your math thing, like the combination thing. Out of the 4 levels, you find the number of unique combinations of using 2 of them. How many unique combinations can you get, right, from 2 of them? So 4C2, 4 choose 2. Denise, are you there? You doing okay? You got IO, is it, or Wednesday, is it? Tomorrow, okay. So the thing is this, I wanted to tell you that if you are you able to do online tomorrow instead of today? Tomorrow 5 p.m. I let you decide because I know how stressful IO can be. Yeah, I know. So it's okay to log off now. Yeah. How about Jamie? Jamie. Okay, so next week then we settle. So why are you doing online? Oh yeah, you're not feeling well. Okay. Denise, go and focus on your IO. Please, you should have just told me that you need time for your IO. Okay? Go, 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 go. See you. Okay. So we have 6 unique photons here. Now the thing about the emission process is that when the electron emits photons, it emits randomly in all directions. It emits randomly in all directions. Right? You get this? Right? Photons will be emitted randomly in all directions. It won't be like, in the same direction where the light is coming in from. So the light comes in this way, for example, it excites, but once it de-excites, it emits photons in all directions. All directions. Can? Right? So if the light is emitted in all directions, right, I want you to think about this thing called the discharge tube or the discharge lamp. Right? Have you heard of that from chem? No? Okay. So in chemistry, they should show you this thing called discharge lamps, which is this one here. Right? These are all, like, they call it the gas filled tubes, right? Or the gas discharge tubes, right? What happens is that these are glass tubes with individual gases inside: helium, neon, argon, krypton, xenon. The gas that we are learning with is hydrogen atoms, monoatomic hydrogen, not hydrogen gas, not H2 gas, right? So we are using all these things. What's happening here is that these gas are all excited now. They're all excited, right? They're all excited. That's why they can de-excite. And when these gases are de-exciting, what do? Emit photons, and that's what they're doing now. They're emitting photons. And in which direction do they emit photons at? In all directions. That's why you can see this tube, and in all directions you can see light coming out from it from all directions.
Does that mean, so there's like multiple electrons inside, because one electron can only emit one photon?
You're right. Yes, that's right. So now my question is, so which photons are possible to come out? Of the 6 unique photons that we talked about just now, right, which photons are likely to come out? All of them come out. Why? No preference. Good. No preference. There's no probability of which one is higher than the other. All of them come out, but why? Because there's that many atoms inside. So the chance of every single photon being emitted is possible. So you don't need to ask at all which ones are going to be emitted. All of them are going to be emitted. Right? So now the next question is this. You look at these colors. Are these monochromatic colors? Monochromatic? What does monochromatic mean? One single color. Do you think that the emission will produce one single color only? In fact, just now we saw, right, from level 4, how many photons does it emit? 6, right? Just from 4 levels, it emits 6 already. So what you're looking at here is likely to be a combination of photons, right? Combined colors. I give you an example. What's purple made of? Red and blue, right? It's just that straightforward, right? If a gas is glowing and it looks purple but not violet, it's purple, right? It's because it's emitting both red and blue photons. That's why it looks purple. Get this? So you look at neon, for example. Neon is like orangey red. So it's likely that neon emits red and orange photons, right? But it's not monochromatic. It's not likely to be monochromatic. It's likely to be a mix of, but a limited number of photons only, like 6. Okay? Okay, huh? You seem very confused. Okay, huh? There you go. So this is how, right, the excited gases will emit the photons, right? And they're emitted in all directions, right? Okay, light production is random. Light production is random.
How do you know whether the color is violet or purple?
No, you don't. You're not expected to predict anything, right? So in physics, we don't need to predict any colors. Yeah. So we just need to calculate the wavelengths, but you don't have to predict what's the outcome. Let's say I ask you, if it produces 2 orange photons, 1 red photon, and 1 blue photon, right? What's the final color? Nobody's gonna ask you. There's no color wheel thing. Yeah. But hang on, to the two of you. Yeah, the two of you. Light production is random. When was the last time I said that? I said it once before, but I don't know whether you remember it. Hmm. Hmm. What? Yes. Good. Right? Yeah. So this thing here ties into your understanding in topic 9 when we say that two light bulbs are incoherent. If you don't understand what that means, I'll have to do that during revision. Okay, because incoherence and coherence is something you need to remember. Okay, all right, that's in topic 9 though. So light production is random. This is tied into something like topic 9, right? Incoherent light bulbs. If you need a marker for this, right? Incoherent light bulbs, right? Light production is random. We okay on this? Can? Right. We'll deal with that later on. So let's look at this picture here again. One more time. Let's look at this cloud of hydrogen atoms. Let me ask you this. Is this cloud being excited? Is it being excited now? No? You don't know? The answer is yes. Yeah. It's being excited now. You nodded. Why? Why? How do you know it's being excited? I mean, it's cool. Yes, I know it's cool. But that's what? What light? What light? What kind of light are you using? White light. White light has what? All the photons, right? It has all the photons. So which means that we are providing photons to the gas. So while this gas is cool, right? We start off with cool gas. Is it being excited now? Is this cloud of hydrogen atoms, is it being excited now? It's being excited, right? And what would it do once it's being excited?
It will relax and then it will release photons.
So it's being excited at the same time, it's also de-exciting.
Yeah.
Right? Yes, that's exactly what's happening. So as this cloud is being excited by the white light, it's also emitting its own light. Correct? And according to let's say for example, you look from level 4, how many photons are being emitted from this cloud of gas? 6 unique photons, right? And in which direction? In all directions. So I'm gonna just ask you to visualize this. I want you to imagine that the photons are being emitted in all directions like this. Correct? Okay. So what happens if you look at or you observe this gas from the side like this? You observe the light that's being emitted from this gas and you pass it through a prism. Right? You pass it through a prism. What would you get? Colored lines on a black background. This is what we call the emission spectrum. Right? Because this is what the cloud of gas is emitting. Right? It's emitting these photons, the unique photons that they absorb. Right? It's emitting the same unique photons. Right? And this is your emission spectrum. Okay? Ken? So your understanding is, be it emission spectrum or absorption spectrum, both spectra give you the same evidence. So it's not like absorption is more evident than the emission spectrum. Both of them are equally, right, on equal grounds, like the evidence for discrete energy levels of an atom. Sometimes, right, the questions will group these two up and call it line spectra. Right, they call it line spectra. Okay? Yeah? So if you see the question, they say explain how line spectra provides evidence for discrete energy levels, right? Then your answer will be exactly this paragraph here, right? Line spectra shows what? Shows specific photons that were absorbed or emitted, right? Due to electron transitions, which are also photons are specific in frequency. So the electron transitions involve specific energy levels, right? Therefore, energy levels are discrete. That's it. 3 marks there. One more time. Yeah, which part? The whole 3 marks thing. No, that is fine. I mean, okay, the first point is not relevant, right? The first point is it provides evidence that they're asking you why does it provide. Yeah, so the 3 points are here, like this one. Okay. No, actually, you don't even need this. The last one here. Sorry. So this two here is equal to 3 marks already. And you know it's IB lah. Right. This amount of detail already considered very good already. 3 marks for you. Any questions? Anything that you encounter in school so far that you don't understand? No? Everyone using hard copy here, right? Or only one soft copy? I sent out a file in the group chat called Quantum, chapter 19. There's a 19.quantum, right? You go and download that file, right, in the WhatsApp group chat. The rest of you have to print it out for you. Right, we're going to do some questions now. Yeah. We're going to do some practice. So practice content, practice content, practice content. But I'm going to take it from the A-level side.
You're gonna take a nap, right?
Take and pass, take and pass. Take and pass.
In the past.
Yeah.
Okay, while I'm waiting for the printout, can you all please look at question 26? Just read the question. I'll walk you through the question 26 in a while. All right, but read through it now. One each. One each. Let me pass one. That looks like a bomb there. That looks like a bomb there. Like I just noticed the red and blue wires. And you have to decide which ones to cut.
Is it?
Yeah. So like I said, again, 26, I'll walk you through it. Right, you read the question. You realize that there are some things that you don't recognize. Right, like say for example C. Let's say you see. Right, photoelectric effect though, some of you who have done the 12.1, you understand what this is for 12.1. But what was the photoelectric effect for? What was the purpose of teaching the 12.1? I mentioned this, I think, in the group chat as well. What was the purpose of learning the photoelectric effect? Yeah, she's right. Okay, so the photoelectric effect is in 12.1. Make a note here. Right, I printed it out for you already. Make a note there. Just understand that the word photoelectric effect is from 12.1, chapter 12.1, topic 12.1, and it's providing the evidence of photons. This experiment, right, provides for the evidence of photons. Right? Did we do that in 7? What did I say in 7? When we were doing that page on photons, I had to force you to accept that light exists as photons, right? Right? I said that last week, right? I said that you have no choice, but you have to accept that light exists as photons. Okay? Because that's a SL thing, right? You do 7, right? You do chapter 7, you start with chapter 7, that's a SL thing. You have to accept that light exists as photons. But what's the proof? What's the evidence in chapter 12.1? Right? So we'll get there later. Right? Yeah, we'll get there later. So we do finish up 7 first. Okay? Right? But that has nothing to do with the discrete energy levels of atoms. Right? Got nothing to do with that. The evidence of photons does not provide the evidence of discrete energy levels in atoms. So C is not an answer. D, let's look at D. Emission of beta particles by radioactive atoms. Now, those who have done nuclear physics already, what's this? What's D? What's beta particles? Is what? It's a high energy electron, but what's the process in which it's produced by? What's that process called? Nuclear decay. Right? Decay, isn't it? Radioactive decay. right? It's decay, right? It's got nothing to do with discrete energy levels of an atom. It's a nuclear decay of the nucleus. Got nothing to do with the electrons, right? So this is decay, right? Okay, let's look at option A. Spectrum of a tungsten filament lamp. What color is a tungsten filament lamp when it's hot? White. White light. Tungsten filament lamp, when it's hot, it's white. When it's cool, cooler, what color? Orange, right? Okay, are you supposed to know that? Guys, are you supposed to know that when something is cooler, it emits orange to red color light, but when something is very hot, it produces white light? Are you supposed to know this for physics? Which chapter? Topic 8, Wein's displacement law. You're supposed to know this, right? It was a topic that was taught last year. Wein's displacement law, W-I-E-N. The one where the graph looks like this. You have a graph like this, and then you have a graph that looks like this. Yeah, you remember the graph. But you have to also remember that the hotter the object is, right, the shorter the wavelength of its maximum intensity, right, and therefore, right, very hot objects will produce the whole spectra, Roy G. Biff, and when you produce the whole spectra, it becomes white. Topic 8, not yet. Yeah, don't worry. I will teach it as a revision, but from what I've heard from Saturdays and Sundays class, I think I have to teach it from almost like from scratch. Right? Either I teach it from scratch or I send you all the videos, okay? All right, that's my thing. Okay. So spectrum of tungsten filament lamp, if it's hot, it's white. What's the spectra called? What's white light spectra called? Continuous spectrum. Right? White light is continuous spectrum, right? White light is continuous spectrum, guys. Here, in this picture here, this one. Right? You take white light, you pass it to a prism, you get all the colors. This is called the continuous spectrum. Why is it called continuous spectrum? Yeah, it's all the colors, right? Is there any missing colors? No, it's continuous, right? But why is it called continuous? What's the opposite of continuous? Good, discrete, right? Discrete is the opposite of continuous. Continuous means that the colors blend into each other. So if I ask you how many colors does the rainbow have, it's not 7. It's a million, right? A few million, a few 100 million different colors, right? That's the continuous spectrum, okay? All right, so white light is continuous spectrum. All right, one more thing, just one more thing about this picture here, right? Because this is something that you need to know. Like I said again, I tell you things that you need to know. When it's something that you don't need to know, I'll tell you, but I'll keep that to a minimum, right? So this is something you need to know. Topic 7, we use a prism because, all right, the SL students don't learn diffraction grating, right? So I'm telling you that instead of a prism, you can use a diffraction grating, right? What does a diffraction grating do? Yeah, split the light. Yeah, you remember this from the topic 9 catch up, is it? Or you knew that from yourself? Right? The diffraction grating splits white light, right, into the component colors. Do you need to know this? Topic 9.4, diffraction grating. Okay? All right, so what I'm going to do is this. I'm going to use this diffraction grating on my projector light. Sorry, I'm going to turn off the light for a while, Emily. Right, so I'm just going to put this thing up here. Right, can you see the wall there? Right? No, you see the left side as well? Sorry, Jamie, you can't see this. Right. Yeah, there you go. Right. Can somebody help me take a photo of this so that I can show Jamie? Yeah, Ethan, you have your phone, right? You just help me to zoom in there a bit, with together with the white color frame in the middle. Yeah, if you can, just kind of like, yeah. I just try to hold it there for a while. Can? Done? Okay. Can you send it to the group? Yeah, good. Can you send it to the group? Yeah, so that Jamie can see it. Guys, I'm not unreasonable one. If you all really got exams, you all got IO, you all got submissions and all that, please let me know. All right, don't overstress yourself. That's not what I want for you all. Okay, so if you all have to either skip lesson or change makeup, or it's just damn troublesome on my side because I need to do a head count.
My bad.
It's fine lah. I'm just kidding lah. I'm just disturbing you. But yeah, all right. So just let me know. I don't want you to be stressed. I think just now she was not feeling very well on the line. I think she's very stressed. Yeah. So just shoot off some encouraging words to her for me. Okay. Right. So that was a white light diffraction grating continuous spectrum. Okay. All right. Diffraction grating. All right. Let's try to do a couple more questions. 29, please come. Yeah. Oh, sorry. Yeah. The answer was B. Sorry. I'm so sorry. Oh, I forgot to talk about the answer. So this one A here is your continuous spectrum. Continuous spectrum is not evidence of discrete energy levels and atoms. Spectra of a sodium discharge lamp. Okay, sorry. This is trivia.
Isn't this like street lamps?
Oh my God, yes, you're right.
Wow.
He's absolutely right. Good. All right. The spectrum of a sodium discharge lamp. Sodium discharge lamps are the sodium vapor lamps for street lights, but they are no longer in use in Singapore. It used to be the orange street lamps.
Those are so nice.
Depends. You like take
Like, in
photos,
the
is it?
neighborhood, but then on the highways.
This is Glendon, damn extra one eh. Glendon damn annoying one eh. Why He just replied and he's okay, I'll kill him, seriously.
Okay.
What the hell? I'm gonna whack him. Okay, yeah, guys, these used to be our streets. I don't know whether you remember, but it took us 8 years to change from this to this. It's all white lights now. Huh? Yeah lah. Okay. Okay. So what's the story behind the orange lamps? Like why is it such a thing? Okay, number one, all right, it's a legacy thing that we took from the UK side. Singapore was part of the UK colony, right? And in the UK they use sodium vapor lamps because orange light, reddish orange yellowish light tends to penetrate through fog much easier. Fog, F-O-G, fog. And the UK, there's lots of fog. The weather is really bad there, right? So it used to like from a safety point of view, it's supposed to help, right? Drivers see better in inclement weather, right? That's why they use orange street lamps, and we just took on that. But guess what? Singapore, not much fog, right? At most you get some haze from year to year. Okay, so we don't get much fog, right? So this whole fog prevention thing is not very useful. The second true reason why they kept on using orange lamps, right? Some countries still use orange lamps is because it's cheaper. In the spectra, Roy G. Biv, right? Roy G. Biv, which ones are the low energy colors? Which ones are the low energy colors? Red, orange, yellow. Of course, you can't use red street lamps. That will look damn creepy, right? So orange, right? So it's a low energy, right? That means lighting up the streets is cheap in orange, right? And they say there's also safer also. I don't know which one is more important. Okay. Then come the advent of LED lamps. LED lamps are really energy efficient. So we use LED lamps now. It's white. Right? There we go. That's right. That's why we've been changing it from orange to white. But here's the thing. What are these lamps made of then? What's inside the lamp on the street lamps here? What's inside? Sodium vapor. It's not a tungsten filament. These orange street lamps, is a glass tube filled with sodium vapor. And they excite the sodium vapor. The sodium vapor gets excited. What does it do? It de-excites and produce orange color light, right? But this is not monochromatic. It's like two colors of yellow and one color of orange. So it's about like 3 or 4 main photons. It's also still not monochromatic. It's also still a mix of colors, right? Sodium is like that. All right. Let me show you a sodium discharge lamp. Okay, sodium discharge lamp. Right, so, oh, lampo, no, lamp. Something like that. Right, it's sodium inside. It's sodium vapor inside the glass tube there. There's no filament. Right, it's just sodium vapor, like Na. Yeah, and they excite it, and therefore it glows. Can? Right, that's trivia. This trivia. But this is, I think, is quite interesting. Right, so I spent about 5 to 10 minutes on trivia. Let's move back on to what you need to know. Okay, so the next thing you need to know for emission and absorption spectrum is that we're done. Yeah, that's it for emission absorption spectrum. There are some questions here. Sorry, I said I wanted to do 29. So let's do 29. We are done with the content. So let's do 29 now. I want to do 29 and 30. So let's do 29 first. Come.
What length actually? Springs.
H,
Yeah,
it's a constant.
it's just
Yeah. When do you use it? I think that's the most important thing.
I think
So look for the equation. Now, of course, flipping through my notes is going to be like a wild goose chase, right? Maybe flipping through the data booklet will be better. All right, everybody got a data booklet. Take one here. Y'all got data booklet there. Data booklet here. You got one? Yeah, take this one. It's fine. Use this. Yeah, use this one. Okay, yeah, that's fine. Huh? Yeah, okay, sorry. 29, answer C. Everyone, C? Jesse, yes, C.
Oh yeah,
Yeah, no, it's okay. I'm just checking your answer. C, Philip, C. Edgar, come. Okay, all right, let me illustrate this for you, Edgar, come very quickly. So between two energy levels, higher to lower, right? But it doesn't matter whether or not it's like from 5 to 4 or from 5 to 3. As long as one is higher, the other one is lower, right? So this is E2 and this is E1, correct?
Yeah.
What does the electron do when it's on E2?
it
It de-excites to E1, and in doing so, it will, right, emit one photon, right? So the question is this photon, right? What's the energy of this photon equals to?
HC over lambda.
Basically E2 minus E1 first, right? It's E2 minus E1, right? E2 minus E1. The energy levels minus the other one, right? Okay, so the energy of the photon is E2 minus E1, and therefore, right, Hc over lambda equals to E2 minus E1. What's the question asking for?
For lambda.
For the wavelength, right? C is your answer. And good. 30. Right, read 30. Go through 30. Wait, 30, yeah. Everyone read. I'll go through this with you in 1 minute's time.
Wait, when you're drawing a diagram, it's not the top is E2, then the bottom is
Yeah, because they did say higher energy level E2 to a lower energy level E1. Was today a very tiring day for you guys? Was it orientation one?
Yeah,
yeah.
the whole week, last week.
Okay. You? Okay. You're right. Yeah, it is A.
Mathematics.
Yes, it is. Yeah, it is. But we have to understand why in detail, right? So, gut feel can't cut it, right? Okay? Hey, just 30 only. Just 30. Just 30. We do until 30 because the rest of it is homework. Yeah, come on. It's fine. Guys, how many times have I said this already? Is my homework is my homework your priority? No. It's your last priority. Huh? I know there's another page. That's homework. Okay. Question 30. A. A. 30. Okay, it's A, huh? Right, let's show you how to do it. Come, Edgar. Right. Guys, I go through this with you because I'm helping you to just be efficient on understanding this, right? It's not that I'm trying to patronize you or cut short your understanding or cut short your learning journey or anything like that. You want to do that, can. 31 onwards, you can even do it at home, right? There are 3 energy levels, okay? Guys, if I tell you there are 3 energy levels, right? How would you draw the 3 energy levels? It's always drawn like that, right? The top 2 are always close to each other. The bottom one is always the furthest away, right? There is no such diagram whereby they draw it for you like this, right? It doesn't make any sense. Okay, but sometimes you still get these kind of questions, right? So you just understand that generically, right, all the energy levels of increasing energy level will be drawn like this: one, then jump, and then a small jump, right? Big jump, then small jump. Subsequent jumps are smaller and smaller, and it doesn't even matter whether this is 1, 2, 3, or 4, 5, 6, or 7, 8, 9. Okay, they're just like one big jump, then a small jump. Okay, they tell you that there are 3 spectral lines produced by transitions between 3 energy levels. Specifically, which one? Absorption or emission? Absorption or emission? Did they say? Did they say is it absorption or emission? No, they didn't say, right? Is it important? No, it's the same, right? It's the same. So these 3 lines here produce, so we just assume that it's emission. It's fine. Okay? So how does these 3 lines produce 3 unique photons? Or would it produce more than 3? Would 3 energy levels produce 3 unique photons, or would it produce more than 3 or less than 3? No, it produce exactly 3. These are the only 3 that you can get from these 3 energy levels. 3C2, punch it in the calculator, you get 3. Right? Okay. So now the question is, of these 3 photons, they are unique because they have different energies. Lambda 1, lambda 2, lambda 3 of increasing magnitude. Lambda 3 is the longest wavelength. Which energy transition is that one? Is lambda 3. Which one? What's the lowest one? I don't understand what's the lowest one. Which one are you talking about? Which one? No, the transition. I'm talking about the transition produces a photon. So which arrow is it? Not the level. The longest one? The longest one would represent the highest energy transition, which will mean the highest energy photon, which will give you the shortest wavelength. So this one produces lambda 1. Okay? Right? So the photon produced by this one is lambda 1. The photon produced by this one is lambda 3. Right? You got to remember that for EM spectrum, energy and wavelength are inversely proportional. Right? Small energy means long wavelength. Jamie, hang on, I need to change my earpiece. Running out of battery.
Longer arrow means
Largest transition, right? Largest change in energy. Okay, so it's not about the level, it's about the change, right? How much it transits by. Okay, there is no direct relationship between lambda 1, lambda 2, and lambda 3, but there is a relationship between their energies. E1 is equals to E3 plus E2. Right? E1 is equals to E3 plus E2. Convert it to the photon equation. Hc over lambda 1 equals to Hc over lambda 2 plus Hc over lambda 3. Right? Cancel all the Hc's, what do you get? 1 over lambda 1 equals to 1 over lambda 2 plus 1 over lambda 3. Right? Answer is A. Yes, you got it right. You change the answer. You got it right also, right? Yeah, you got it right. So, Jesse, what was your thought process when you were doing this? Was it the same?
It's just very important. But I understand.
Okay, so this, I think the important thing that I wanted to touch on was this part here. The part where the shortest energy transition, the smallest energy transition will give you the longest wavelength. Because this question here is a very common trick question. Like if I were to see any exams or any tests come out, right, at least this will come out. This one of these questions will come out. Okay, all right. So I can't spend time doing all the practice questions, but there are practice questions here. So from 31 to 36.
Wait, do you get it your annotation?
Oh, hang on.
E equals to,
Wait, hang on. Wait. Okay, wait.
sorry.
No, it's fine. Let's just bring it up first.
Okay.
This one here. Yeah. 31 to 36 is your homework. Right? Just with all my other homeworks, it's last priority. What's your first priority? Oh, okay, yeah, IO, yeah, okay. And your school homework, don't get in trouble with your teachers. If your teacher asks you to do assignments and you don't do it and they threaten you, start saying that I'm gonna tell you I'm gonna report this to your parents, then you just do the homework first. Okay? Alright. Guys, you all know that you all have the answers, right?
Yeah.
Right? It's in the chat, sorry, the ACSI guys. Right? You all know that your answers are inside the chat drive, right?
Yeah.
Your school homework answers. Yes, here. You go to the shared drive.
We don't have school phone.
No lah, if they ask you to do lah, right? If they ask you to do, huh? Oh no. But it's inside lah, okay? Alright, so if you want to do your school questions, you can go inside and do your school questions. There are two folders there. Right? The mark worksheets and the topical questions. It's in the group description of the WhatsApp chat. Yeah. Okay? I corrected it already. I wanted to see who will prepare for the test. Nah, it's tough lah. I know this period of time you guys are dying on lah, so go easy on you guys. Okay, so the rest of that was homework, so please go and get it done. Let me just do a quick check. Okay, hang on. Yeah, so this last thing, I just want to make sure I seal it in, right? 38. It's not in your, it's not printed for you, right? 38. I just want you to do 38. Look at the board, do 38, and tell me what's your answer. What? What do you say, Caleb? Don't think like earpiece here. I can hear you. I can hear you.
Is it dark lines or
Yeah, you're right. It's dark lines on a color background. Okay? So a beam of light from a tungsten filament lamp. What are they trying to say here? A beam of light from a tungsten filament lamp. What's that? It's white light. White light is passed through sodium vapor. So it's passed through a cloud of gas. Right? Before it is incident. That means the white light passed through the gas already, then it goes incident on the diffraction grating. What does the diffraction grating do? Split. Right? So this question here is in my notes, like looking like this. Right? Is basically this top part here. Tungsten filament lamp, white light goes through the gas, right? Some photons will be absorbed, the rest of it will pass through before it's incident on the prism or diffraction grating, then it's split, right? Then you see black lines on the color background. C is your answer for that. Okay, now disclaimer, one quick disclaimer. So can you all flip to this page? I forgot to do this page here, this one here. Okay, flip to this page here. So some students have asked me before, they're very confused by this, like by this picture, okay? This picture is just an adaptation of what you see, like a very simplified diagram from school. Okay, I'm gonna tell you this. So some students have asked me, but isn't the white light touching this prism? And if the white light is touching this prism, then wouldn't this be the continuous spectrum also? Then okay, fine, yes. The whole point of this diagram was to show you that I'm only looking at the gas, right? So go and draw a wall here. Go and draw a wall here, block the white light, okay? Go and draw a wall here, please. Okay?
We just accept it.
Just in case lah, okay? Right, draw a wall here, right? The white light is being blocked, okay? Right, you get the spectrum here, okay? Right, draw the white light.
See all
But passing it through sodium,
Come, tell me.
then why is like how you know it's absorption and not emission? I don't know how to tell. What's happening? When you pass it through sodium, what's happening?
Huh?
When you pass it
Pass what?
light.
White light. Is it white light?
I mean, following the question, right?
Yeah.
When you pass it through the.
If it's white light has what? No, white light has what? White light. What does white light have? Yeah, how many? How many different photons? All the photons, right? Yes, you're right, all the photons, okay? And I'm gonna let all the photons pass through sodium gas, right? Sodium vapor gas, right? But of all the photons that passes through the sodium vapor gas, which ones gets absorbed? Some orange, right? A few orange, maybe some red, right? Like specific ones, right? Yeah, it is. Yes.
Oh.
Sodium absorbs the photons that it emits. Jesse, look at these two pictures here. They are complementary. You take one of them. You take. Oh, sorry. Wrong two pictures. Yeah. You take this one, right? You bring it over to here. It fits nicely in the jigsaw puzzle.
Yeah.
Yeah. Because the photons that were absorbed are the photons that the sodium vapor emits. Because of the levels. Remember when we deal with 4 levels, right? When we were exciting it, when we're trying to excite it, how many unique photons does it absorb? 6. When it's de-exciting, how many unique photons does it emit? 6. It emits the exact 6 photons it absorbs.
So sodium both emits and absorbs.
Yeah, correct.
Then how do you
But
test absorption?
okay, so absorption spectrum, right? Jesse, absorption spectrum, right? You require white light. You see the white light? The white light passing through here. The white light going through. So what is happening here? Like, don't care about the emission. Just think about the absorption here. White light passing through this cloud here, right? What's happening? What's the process happening here first? Absorption. How many gets absorbed? How many photons get absorbed? Not just one, a few, right? But a few unique photons, right? Okay. What comes out? Here's the important part. That's where your confusion is. What comes out here? No, what comes out here? This one. You see, it's white light that's passing through. Jesse, one more time. Hang on. White light passing through the cloud. What's happening here? Only some are being absorbed, right? What happens to the other photons?
Oh.
What happens to them? Yeah, what happens to them? They just pass through. They don't get absorbed. Right? So when you're in this direction, because this is the line of the white light, right? This is the line of. So this is full white light.
Oh, yeah.
All colors. This is still white light, but missing some colors. So when I still consider white, correct?
And if there's nothing else that absorbs like more than just orange, you'll still be
Yeah, it's pretty much just white. Because if you can get all the millions of colors, but you're only missing a few, it's still generally white.
okay.
But once you split it, you will see, they are missing colors. That's your absorption spectrum. Okay? So the question is, how do you, no, wait, hang on. How do you observe the emission spectrum? Guys, listen, this is a very important thing that she brought up, okay? Because this is something that usually when people start asking questions, I will clarify. So I'm clarifying it now, because since the question has come up already. Can I observe the emission spectrum in this direction? Can I see the emission spectrum from this direction? Why not? Why can't I see the emission spectrum from this direction? Because it's generally white light passing through, right? The colors will all appear like this. How do you get the emission spectrum? That means you only want to see the light that the gas emits. Since it's excited now and it's emitting, where is it emitting in? All directions. So it's emitting in all directions. So I just choose a certain direction. I split the light that's coming from this gas here. If it's sodium vapor gas, this cloud would look a bit orange. Right? Then I split it. Then I would see orange, red, yellow. Right? That's the photons that will appear. That's the emission spectrum. Right? Devoid of any white light. There's no white light here. You get this? There's no white light. There's only the colors.
But how do you get rid of the white light? Like, just like talking about this thing, right?
Yeah. That's a wall to block the white light from touching the prism there. That means I only want to see the light that's produced by the gas. It's a wall. It's a wall. Wall. W-A-L-L.
Okay.
W-A-L-L.
So it's only cause you block the white light.
Yeah, I'm trying to block the white light.
The orange, yellows, whatnot.
From the, yeah, okay. Hang on, Hey, wait. One more detail. Guys, okay, since you keep answering this, I'll make you answer again one more time. Emission, in which direction? All directions. So, am I right to say that if I want to see the emission spectrum of this cloud, I can view it from any of these directions here, except in this direction, in this direction, because this is the white light going out, like this. That's not what you want, right? You don't want to see the Huh? Why the white light can come out? That was the same question that she was asking just now. White light from the lamp, the white light passing through. What happens here? Only some photons are absorbed. What happens to the other photons? They pass through. And therefore, since it's mostly all the other photons and only some photons missing, this is still generally white. Right? And this is your absorption spectrum. Emission spectrum is everywhere here, guys. Right? Anywhere here, because we're just viewing the gas as it emits a glow. Okay? All right. One more small little detail. Is it possible that the gas emits the photons in the same direction as the original direction? It is. It's absolutely possible. Right? So why doesn't it appear on the black lines here? You understand what I'm saying? Since this gas emits photons, right? And I said it, you said it many times also, it emits in all directions. So can it also emit in the same direction here? Can, right? It is possible. So how come they still look black? Because of the intensity. It's not as bright as the other colors. It's not as bright as the other colors. This is white light. All these colors here are all white light. Right? These lines here are not completely black. They are just very dark. Okay? They're just very dark lines. But that's a small little point. I don't need you to go and write this in an exam. It's just, if you are studying and you ask me this question, I have answered you. Right? When you're studying and you start asking questions, why is it like this? Why is it like that? How come it's not going in the same direction? I've answered you already. Right? This is me just anticipating all the questions that will come out in the future. Because I know these questions come out all the time. So I'm just answering you in advance. Okay? Can? Alright. One small thing. Yes. Random, yes. No, it's not a black body. What's a black body? A black body is a perfect. Black body is a what? Perfect emitter and a perfect absorber, which means that whatever you throw at it, it will absorb. So it's absolutely not a black body. Yeah. You know Vanta black? Yeah, you heard of it before many times, right? Vanta black is so black that any kind of radiation you throw at it, it will absorb all the radiation. Okay? Can? Yeah, there you go. Wait, hold on. One last thing here, guys. Okay. You're gonna burn it out. I'm not that familiar with them yet, so don't. You cannot mention his name when I'm drinking water, bro. Tila. I will spit water on. I'm recording this, I'm gonna clip this. Every time I say his name when I'm drinking water, I'm bound to spit water. Okay, this page here, okay? Just humor me for 3 minutes. Right? Look at the title of the page. It says good to know. Right, good to know. So far, what have we been doing to excite the atoms? What have we been trying to do to excite the atoms? Like, how do we excite atoms? Shine what? Shine white light on the gas, right? Okay? So far, all we've been doing is we shine white light. So what's the caveat for shining white light? The gas will only absorb specific photons to excite, and when it de-excites, at the same time, it will emit the same photons in all directions, correct? Right? We are using white light to excite. There are other ways to excite the atom. Right? One of the more generic ways is to just zap it with electricity. That means you just fire electrons at the gas. Right? That means we're not using white light to excite the gas. What are we doing? Just zap it with electricity and electric current. See? Electrons, electricity. I shoot it at the atoms. But the process is still pretty much the same. What happens to the electrons once they're excited? What happens to the atoms when they are being zapped by the electricity? They will de-excite, and what will happen to the gas? What will the gas do? Emit photons in all directions, correct? Okay. What's the point of this page? The point of this page is this. I'm going to ask you this question. You think about this. Can I get an absorption spectrum from this process? Can I get absorption spectrum from this process? Think first before you answer. Can I get an absorption spectrum from this process? Edgar shaking his head. You also shaking head. You? Also no. Still thinking. Absorption spectrum. Can you get an absorption spectrum from this process? Come, Edgar, tell me why. Why you say no?
There's no white.
Good. That's the whole point. Absorption spectrum needs white light. I'm not using white light here. What am I doing? I'm zapping the atoms with electricity. Okay? Right? There's no absorption spectrum to speak of here. Now, I'm going to tell you this, okay? Why do I put good to know? This is good to know for your school exams. Your school may ask you this question, which is super unfair because this is not in the IB syllabus. Right? Zapping the atoms with electrons, right? Making the electrons excited using electricity is not an IB thing. That's why I say it's good to know. But just in case your school test comes out and you're wondering, what the heck are you doing? Where's the white light? Right? Because there are other ways of excitation. There's actually a third way of exciting your atoms. So one is white light, second is electricity. What's the third way? Just make it hot. Take a blowtorch, hot, you'll glow. That makes sense, right? Once the gas is heated up, it'll glow. Right? But you don't learn that. All right, that's fine. Okay, so now you know about this. Can? Right. So what can you get out from this though? You can get the emission spectrum. You can't get the absorption spectrum. You can get the emission spectrum. Why? Because it emits. In fact, that's how the orange street lamps work. Right, Edgar, you were talking about the orange street lamps. What do we zap it? What do we do to the sodium? We zap it with electricity, all right? We pass a current into it. That's how the atoms get excited and they glow. Okay?